of all, I'd like to thank the organizers. Okay, thanks the organizers for giving me an opportunity of this talk. Today, I'd like to discuss the geometry of a projective manifold with pseudo-effective tangent bundle. Okay, this is a joint work with Genki Hosono and Masataka Iwai. Okay, today, this talk gives a structure theorem for a pseudo-effective tangent bundle in section 2, and after we review the previous works, classical works, in section 1. In section 3, I explain idea and the sketch of the proof. In section 4, I want to explain examples of pseudo-effective tangent bundles to classify all surfaces with pseudo-effective tangent bundles. Okay. In this talk today, let X be a smooth projective variety over the complex number field of dimension n, and we denote by Tx the holomorphic tangent bundle of X. Okay. Roughly speaking, today's goal is to generalize the structure theorem for Neff tangent bundle to a structure theorem for pseudo-effective tangent bundle. This condition of having Neff tangent bundle means, roughly speaking, X has non-negative curvature or smooth metric. On the other hand, this condition, having pseudo-effective tangent bundle, means X has non-negative curvature or for a singular metric or some singular metric. I will explain the precise definition later. Okay. Study of certain positively curved variety is originated from Frankel conjecture proved by Xu and Yang, and Frankel conjecture proved by Mori. Let's start from a brief history. Frankel conjecture said that if tangent bundle is Griffith positive, which means tangent bundle has metric with Griffith positive curvature, then X should be biholomorphic to the projective space. Hudson conjecture is an algebraic counterpart of the Frankel conjecture. Hudson conjecture says that if tangent bundle is ample, then we can get the same conclusion. Okay. These theorems are the perfect classification for positive tangent bundles. The next natural problem is to generalize these results to non-negative curvature. This is very natural question, okay, which were done by Howard Smith-Wu and Dumari, Peternel, and Schneider. Okay, Howard Smith-Wu proved that if tangent bundle is Griffith semi-positive, then X satisfies good structure theorem. I will explain that. I will explain detail later. Okay. Dumari, Peternel, Schneider consider Neff tangent bundles. A Neff tangent bundle is an algebraic counterpart of Griffith's semi-positive tangent bundles. And they proved that if tangent bundle is Neff, then X satisfies the same structure theorem as in Howard Smith-Wu. Okay. Today, I want to introduce generalizations to singular metrics. Okay. I want to consider singular positively curved tangent bundle and pseudo-effective tangent bundle. And I want to explain some structure theorem under these assumptions. Okay. Okay. We reviewed the previous works for Neff tangent bundles and Griffith semi-positive tangent bundles. Okay. We assume that tangent bundle is Griffith semi-positive or Neff. Okay. Then X satisfies good structure theorems. X has fibration to the projective variety Y. Here, fibration phi is surjective holomorphic map with connected fiber. Okay, X has good fibration, satisfying three conditions. First conditions, Y is torus abelian variety up to finite étale cover. There exists finite étale cover of Y, whose covering space is abelian variety, torus. Okay. The second condition, okay, phi, fibration phi is locally trivial, which means all the fibers of phi are isomorphic each other, biholomorphic each other. In other words, the complex structure of the fibers doesn't change. Okay. Third condition, F, which is a fiber of phi. The fiber of phi satisfies two conditions. First condition, tangent bundle is Griffith. Tangent bundle is Griffith semi-positive or Neff, respectively, depending on the first assumption. Okay, F is a Fano manifold, which means its anticanonical bundle is ample. In other words, anticanonical bundle has a positive curvature. Okay. Of course, the next problem is the geometry of fiber satisfying these two conditions. Mock proved that if F is a Fano manifold with Griffith semi-positive tangent bundle, then F is Hermitian symmetric space. Okay. If F is a Fano with Neff tangent bundle, then F will be homogeneous. This is an open problem in the higher dimensional case, which is called Campana-Peternel conjecture. Anyway, roughly speaking, this theorem says that variety X with Neff tangent bundle can be decomposed into torus Y and Fano fiber F. Okay. Okay, let's recall the positivity notions for vector bundles. Okay. I want to define positivity notions for vector bundles. Let E be a holomorphic vector bundle on X. Okay. Then I want to define Griffith semi-positive vector bundles, Neff vector bundles, possibly singular, positively curved vector bundles, and pseudo-effective vector bundles. Okay. First of all, let me explain a relation of them. First condition implies second condition, but the converse is not true. Third condition implies the fourth condition, but the converse is not true. Okay. The third condition and the fourth condition are the generalizations of the first one and the second one to singular metrics. And first one and the third one are the positivity notion in differential geometry by using the curvature. On the other hand, second one and the fourth one are the positivity notion in algebraic geometry. Okay. We start from Griffith's semi-positive vector bundles. Okay. Vector bundle E said to be Griffith's semi-positive if E admits smooth Hermitian metric G, satisfying that the curvature tensor associated with G is non-negative in the sense of Griffith. I don't explain the curvature. I don't explain the definition of the curvature. In this talk, we need only this inequality. In this talk, we need a characterization of this inequality by using condition star. What is condition star? Okay. Condition star is saying that for any holomorphic section of the dual of E, S is a local holomorphic section of the dual of E. We consider the function defined by logarithm of the norm of S with respect to dual metric. Okay, and this is PSH. This is condition star. Okay, condition star characterize this inequality without using curvature. Okay, in the statement of condition star, there is no curvature. Without curvature, we can characterize this inequality. This is key point. Then we can easily define positively curved vector bundles. E is said to be positively curved if the vector bundle E has a singular Hermitian metric with condition star. Okay. I don't explain the detail of singular metrics. Roughly speaking, this is a non-smooth metric. Anyway, if E has non-smooth metric satisfying condition star, we say E is positively curved. Okay. The difficulty in studying singular metrics on vector bundles is we can't define curvature for singular metrics on vector bundles. Okay, we can't define curvature. We can't define curvature, but we can define this inequality by using condition star, because as I said, in the statement of condition star, there is no curvature. There is no curvature in this statement. Okay. Anyway, and this is the definition of positively curved vector bundles. Okay. Okay. Next, I want to define Neff vector bundles and pseudo-effective vector bundles. For this purpose, we consider the projective space bundle, PE. And this is the set of all hyperplanes of E. And we consider tautological bundle. We denote by LE. Okay. Okay. The LE, this LE is a line bundle on the total space PE. Okay. we can define neffness. Okay. E is said to be neff if the line bundle LE is a neff line bundle on the total space PE. What is the definition of neff line bundles? Line bundle L is said to be neff for every epsilon. There exists smooth Hermitian metric on line bundle LE whose curvature tensor is larger than minus epsilon omega. Here, omega is a fixed Taylor form on the total space. This inequality says that negativity of the curvature tensor is smaller than epsilon. Okay, if we can take the curvature with arbitrarily small negativity, then we say L is neff. And this condition is equivalent to algebraic notion. For every curve in PE, intersection number is non-negative. Okay. This is the definition of neff vector bundles. Okay. Similarly, we can define pseudo-effective vector bundles by using two conditions. First condition, LE is a pseudo-effective line bundle on the total space PE, which means that there exists singular metric on the line bundle LE, whose curvature current is non-negative. In other words, LH satisfies condition star. Okay. Some papers define pseudo-effective vector bundles by using only first condition, but we require the second condition to define pseudo-effective vector bundles. We require the second condition. We consider the B minor of LE. B minor is called non-neff locus of LE, which is countable union of a Zariski closed set of PE. Second condition says that the non-neff locus is not dominant over X. Namely, image of non-neff locus is properly contained in X. Okay. What is the non-neff locus? The non-neff locus is the variant of base locus of L. This is defined by union of the stable base locus of ML plus A. Here, FA is a fixed, sufficiently ample line bundle on a total space PE. Okay. I have to say line bundle is neff if and only if B minor is empty. Okay. And we have characterizations of pseudo-effective vector bundles. E is pseudo-effective if and only if symmetric product of E twisted by ample line bundle A is generically globally generated. Okay. By the same way, we can characterize neff vector bundle for any M. This vector bundle is globally generated. Okay. It's not easy to check pseudo-effectivity of vector bundles because when we check pseudo-effectivity by using right condition, the rank of this vector bundle is larger than larger when we when we take sufficiently large n. So it's not easy. It's not easy to construct pseudo-effective vector bundle or vector bundles. Okay. Anyway, this is the definition of pseudo-effective vector bundles. Okay. Okay. Let's take our main result, structure theorem for pseudo-effective tangent bundle. Okay. We assume that Tx is singular positively curved. Sorry. We assume that Tx is positively curved or pseudo-effective. Then we can get the fibration from x to y, satisfying that y is torus, abelian variety up to finite total cover. The first condition is completely same as in the previous works, classical works for F-tangent bundles. Second property. If we assume tangent boundary is positively curved, then we can show phi is locally trivial. Okay. If we assume that tangent boundary is pseudo-effective, then we can show phi is smooth. In other words, submersion. Okay. Next, we consider fiber of phi. F is a general fiber of phi. Okay. General fiber phi satisfies two conditions. Okay. Tf is positively curved or pseudo-effective, respectively, depending on the first assumption. Okay. And f itself, f is not necessarily Fano. F is not always Fano, but we can show that f is rationally connected. For short, we say RC. What is a rationally connected manifold? F is said to be rationally connected if f has many rational curves. Strictly speaking, for any 2 points in Y, we can find a rational curve. We can find holomorphic map from P1 to X, whose image passes through X and Y. Such a curve, the curve which is the image of P1 by holomorphic map, is called a rational curve. Okay, this is rational curve. Okay, if we can find the rational curve passing through any 2 point, we say f is rationally connected. Fano manifold is always rationally connected. A Fano manifold is always rationally connected. The converse is not true. Converse is not true, but roughly speaking, RC manifold is a Fano-like manifold. This theorem tells us that X with pseudo-effective tangent bundle can be decomposed into torus Y and Fano-like variety, Fano-like fiber F, rationally connected variety F. Okay. And this theorem is very similar to the classical works for F-tangent bundles, but there are essential differences. Okay, let me explain difference and related open problems. A related open problem is interesting, I think. First open problem. Okay. If we assume tangent boundary is pseudo-effective, then can we show that P is locally trivial? And this is the first open problem. If we assume that if we start from positively curved tangent bundle, then we can show phi is locally trivial. But when we start from pseudo-effective tangent bundle, we don't know whether or not can we prove phi is locally trivial. Okay, if tangent bundle is F, this is true. Why? What is the reason? If we start from F tangent bundle, then we can get splitting of tangent bundle. Okay. From this splitting, we can conclude that phi is locally trivial by using foliation theory. Okay. The key point here is we can get splitting of tangent bundle. Okay. But however, when we start from pseudo-effective tangent bundle, we cannot get splitting. There exists a counterexample. I will explain this counterexample in section 4. Okay. Anyway, we can't get splitting, but it may be expected that phi is locally trivial. Okay. This is first question. The second question is related to positivity on the canonical bundle on fiber. Can we prove that anti-canonical bundle on fiber is weak? This is the second question. If tangent bundle is F, this is true because fiber is Fano. The reason why we can prove fiber is Fano, if tangent bundle is F, and if F is rationally connected, then we can show that anti-canonical bundle is big. Then we can prove that fiber is Fano, thanks to Neffness of tangent bundle. Okay. If we start from pseudo-effective tangent bundle, we can't conclude ampleness, but I think we may expect that the anti-canonical bundle is still big. This is the second question. A typical example of pseudo-effective tangent bundle is toric variety. If X is a smooth toric variety, smooth projective toric variety, then tangent bundle is generically globally generated. In particular, tangent bundle is pseudo-effective, positively curved. Then anti-canonical bundle is weak. So at least when we consider a typical example of toric varieties, this question is true. But I don't know the general situation. Okay. Next, let me explain the idea of the proof of our structure theorem. Okay. Proof. Okay. For the proof, we consider MRC fibration of a projective variety with pseudo-effective tangent bundle. We consider a MRC fibration of X. What is MRC fibration? MRC fibration is maximally rationally connected fibration. Okay. Our strategy is to prove that we can choose holomorphic MRC fibration, and the holomorphic MRC fibration satisfies all the conclusions in our structure theorem. Projective variety X always has MRC fibration. Existence of MRC fibration proved by Campana and Koramira Okamori. independently. This is a classical work. Okay. First of all, let me explain RC fibration. RC fibration is a rational map satisfying two conditions. First condition, P is an almost holomorphic map. Namely, P is rational map, not always holomorphic map, but P is rational map whose general fiber is compact. Let me draw the picture. Okay, we have X, we have Y, we have rational map. P is not always holomorphic, so P has indeterminacy locus on which we can't define phi as holomorphic map. Special fiber. When we consider special fiber, like this picture, special fiber is non-compact. In other words, special fiber intersect with indeterminacy locus, but general fiber is compact. Okay. In other words, general fiber doesn't intersect with indeterminacy locus. This is an almost holomorphic map. Okay. RC fibration is an almost holomorphic map whose general fiber F is rationally connected. Okay. So fiber F has many rational curves. Okay. X has many rational curves in vertical direction, like this picture, because general fiber is rationally connected. Okay. What is MRC fibration? MRC fibration is an RC fibration satisfying third condition. Roughly speaking, third condition says that X has few rational curves in horizontal direction. Okay. Third condition is X has few rational curves in horizontal direction. Okay. This is an MRC. This is a definition of MRC fibrations. MRC fibration is unique up to birational models of Y. Okay. If we take resolution of singularity of Y, we may assume that Y is smooth. Okay. There are ambiguity of the choice of MRC fibration. So if we take resolution of singularity of Y, we may assume that image Y is smooth. Then third condition can be replaced by the existence of rational curve on Y. Third condition can be replaced. Y is not covered by rational curves. And this is proved by the deep result proved by Grave-Stahl-Hayes. They proved that any rational curve in Y can be lifted in X. Okay. If Y was covered by rational curves, if Y has many rational curves like this picture, we can find many rational curves in horizontal direction by lifting them by using their results. Okay, so we get this equivalence. Also, we can replace this condition by the canonical bundle of Y. This condition is equivalent to the canonical bundle is pseudo-effective. This is also very famous result proved by Bookson, Jumari, Pan, Peternel? Peternel pan? Yeah, pan peternel. Okay. Anyway, in summary, MRC fibration is an RC fibration whose fiber is rationally connected to Y with pseudo-effective canonical bundle. Okay. Our purpose, our strategy is to find holomorphic MRC and show that holomorphic MRC satisfies the all conclusions of our structure theorem. It's a little bit complicated to choose holomorphic MRC. So for simplicity, for the proof, for the simplicity, for simplicity, we assume that phi is holomorphic and smooth. Okay, under this special assumption, we will show that Y is torus. Yeah, proof is not difficult. Okay. Anyway, we are assuming that our MRC is holomorphic and smooth. Okay. Then we consider the exact sequence, standard exact sequence of tangent boundaries. Okay. And we are assuming that Tx is pseudo-effective. Then we can easily check that quotient of pseudo-effective vector bundle is always pseudo-effective. So this quotient, pullback of Ty, is pseudo-effective. Next, we consider the first Chern class of quotient. This is 0. This is because first Chern class of the pullback of Ty, this quotient is the pseudo-effective vector bundle. The first Chern class of pseudo-effective vector bundle is always pseudo-effective. On the other hand, this one is minus pullback of the first Chern class of Ky. Here, we have Ky, canonical bundle. By the MRC fibration, by definition of MRC fibration, Ky is always pseudo-effective. So this is pseudo-effective. So our first Chern class is pseudo-effective. And minus our first Chern class is always pseudo-effective. So first Chern class should be 0. Okay. Then we consider following up. We consider the first key. We consider the first key lemma. We consider the first key lemma. Okay, I explain a general statement. The general statement will be used in the next step. Okay, we consider reflexive sheaf on X. Okay, and we assume that E is a pseudo-effective sheaf, and the first Chern class of E is 0. Then we can show that E is actually locally free sheaf and numerically flat. So, namely, E is Neff with vanishing first Chern class. Let's apply first key result to our tangent bundle of Y. Okay, our quotient is pseudo-effective, has 0 first Chern class. So by applying first key result, we can conclude that this quotient is actually numerically flat. From this flatness, we can conclude that Y is torus up to finite data recovers. Okay. Okay. Next, let me explain idea to choose holomorphic and smooth MRC fibration. Okay. Next, let me explain rough idea to choose holomorphic and smooth MRC fibration. Okay. This idea is based on the Cao Herring's work. Okay, and the basic idea is to repeat above argument on a Zariski open set. For reflective series, not vector bundles. Okay, let me explain. Okay, we first take arbitrary MRC fibration phi. Phi is not always holomorphic. Okay. Then we take Zariski open set Y0 and we consider its inverse image. Phi is almost holomorphic. So we can find Zariski open set Y0 so that restriction of phi to X0 is morphism, holomorphic map. By generic smoothness, we may assume that phi0 is smooth morphism by taking smaller than by taking smaller Y0, we may assume that phi0 is a smooth morphism. Okay. By repeating this argument on Zariski open set X0, we can conclude that pullback of Ty is a pseudo-effective, has vanishing first chunk, zero first chunk class. Strictly speaking, this is not vector bundle a priori. Let me explain. The pullback of Ty, okay? Pullback of Ty is defined only on Zariski open set X0, okay? This one is an extension of this locally free sheaf to a reflective sheaf on X, okay? And this is not vector bundle. This is sheaf on X. Okay, this is an extension of usual pullback to a reflective sheaf on X0. By repeating above argument, we can conclude that this one is a pseudo-effective sheaf with vanishing first chunk class. Then, by applying first key results to this sheaf, we can show that this one is actually locally free and numerically flat. Then, from this locally freeness and some lemma due to Dumari Peternel Schneider, we can conclude that this one, relative tangent bundle, which is defined only on X0. Okay, relative tangent bundle can be extended to a sub-bundle, not a sub-sheaf of Tx, which means that relative tangent bundle determines the foliation of X. Okay. From this foliation, by using the theory of foliation developed by Herring, we can find holomorphic MRC. We can construct holomorphic and smooth fibration to Y prime. Y prime is the leaf space of constructed the foliation. Okay. This is another MRC fibration. Okay. This is a rough idea to choose holomorphic MRC fibration. Okay. Okay. Finally, I want to explain how to get local tubularity of phi under the stronger assumption that Tx is positively curved. Okay. Here we prove second key results. We consider the exact sequence of vector bundles. E is, and we assume that E is positively curved, and the first Chern class of Q is 0. Then this exact sequence splits. Okay, by applying second key results to our situation, we can show that tangent bundle splits. So we can conclude that P is locally trivial. Okay. I have to say so. If E is Griffith semi-positive, I mean E has a smooth metric with positive curvature, then this key result is obvious, trivial. Because when E has a smooth metric, we can compare the curvatures between E and Q and S. Okay, then we can easily get the splitting by the classical results. But when we consider singular metrics, we can't define curvature. We can't define curvature, but we can prove the same. We can prove the same conclusion. And Heikon Passionel recently proved that second key result is true under the additional assumption that E satisfies minimal extension property, which comes from the property of L2 extension theorem. Our contribution is to remove additional assumption. Okay. Finally, let me explain examples. To construct examples of pseudo-effective vector bundle is not easy. Let's classify all the surfaces X with pseudo-effective tangent bundle. Okay. We consider MRC fibration satisfying our structure theorem, and we consider the three cases. Dimension of Y is 2 or 1 or 0. Okay. First case, X is Y and Y is torus. There is nothing to study. Okay. Next, second case. Second case, X is P1 bundle over elliptic curve C. So X is projective space bundle of E of rank 2. Okay. Third case, X itself is rationally connected. Then, by the classification of surface, F is the Hiltebrough surface or its blow-ups. It's a sequence of blow-ups of Fn. Okay. Okay. We first focus on the second case. Second case, okay, let's consider P1 bundle over elliptic curve C. Then we may assume that E is one of the following. Okay. E is the product of E is the direct sum of trivial line bundles and positive line bundle. Here, P is point in C, N is a positive integer. Second case, E is the direct sum of trivial line bundle and L. L is numerically trivial line bundle. Okay. Third case, E satisfies exact sequence. And this exact sequence does not split. Okay. By the classical works, in the second case and the third case, tangent bundle is nef. The problem is first case. Problem lies in the first case. In our work, we consider the first case in detail, and we proved that tangent bundle in the first case is pseudo-effective, but not positively curved. And tangent bundle does not split. Okay. The proof is just computation. Proof is just computation. We compute the section of X of the symmetric product of Tx twisted by some positive line bundle by using Weierstrass function on C. In my feeling, the proof of this proposition is more difficult than our structure theorem, our main result. This is just computation, but very hard computations. Okay, anyway, we can classify surfaces in second case. Problem is third case. Okay. We consider irreducible surface. Of course, irreducible surface is projective space bundle of this ranked vector bundle. Okay. It's so difficult. It's so difficult or impossible to classify all blow-ups at the special points. So we consider only general points. I mean, let sigma be general k points in irreducible surface. This is the set of general k points in irreducible surface. And we consider the blow-up of irreducible surface along sigma, general k points. Okay. In our work, we studied this X. And we can conclude that tangent bundle is actually generically globally generated if k is smaller than or equal to 2. In particular, Tx is positively curved. Okay. And if k is 3, tangent bundle is pseudo-effective, but not generically globally generated. Okay. Then k is 4. In this case, this case is still open. If k is larger than 5, then Tx is not pseudo-effective. If we can solve this case, we can classify almost all surfaces with pseudo-effective tangent boundary. The proof of this proposition is based on computation. The computation of this one is more hard than this case. Actually, we use the computer to check to construct good sections, generating general points. Okay, I will stop here. Thank you.
Thank you very much for the talk. And now it's time for questions and remarks.
Yeah. So Shin-ichi, so I have one question. So for your last proposition, so in the case 1k equals to 2 or 3, so you can also prove that for its anti-canonical bundle, it's bigger, right?
Anti-canonical bundle?
Yeah. For its anti-canonical bundle, yes. So for
all cases.
Yeah. So for the blow up, so for the blow up for FAN, so we know that 1k is less than how many? It will bigger. When we start from
sorry. Okay. I see. Sorry. So okay. 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 We have a P2. 1 point blow up P2. 1 point blow up of P2 is F1. F1.
Okay.
Yeah. So we consider the 9 points blow up.
Yeah. So for this one, it's
this one. Yeah.
It's not big.
Yeah. But okay. The blow up at 8 point blow up has ample anti-canonical bundle. Yes. This is 9 point blow. This is 7 points blow up of F1. Okay. When we consider blow up of F1 at 7 points, this variety has ample anti-canonical bundle. But when we consider 8 point blow up, does not have ample anti-canonical bundle.
Yeah. In the case for FN, so we have some similar. So for
N, if n is large, then anti-canonical bundle of the blow up of suitable surface is still big.
Yes.
If k is small, but has singularity, not ample.
Okay. So means that for enlarge, so we know that if we blow up also less than 8 point, its anti-canonical is still bigger. Okay, I see.
Yes. At least when we consider blow up of suitable surface, we can check second question.
I see. So in this case, so essentially, so for the second question, it holds 1x is of dimension 2. So for
at least when we consider general blow.
Yeah.
I don't know special blow.
I see. I see.
Mm.
I see. Thank you.
Mm-mm.
Yeah. Okay. I see. Thank you.
Some other questions or remarks? Okay, there seems to be no more questions. So thanks again for the wonderful talk.
Thank you.